Okay, so we will continue where we ended. We are here now on, I think I ended on the part where we need to factor out the V sub S over R. And we have the V sub S and the R substituted already here. And our current for the RL circuit that was shown to you is zero point 0.1 times the quantity 1 minus E raised to negative 50t. You have noticed, class, that in all the examples that I have given, I've shared with you, the K is always determined. That this K here, the K in the original DE, or the original evaluated DE, this constant of integration is always evaluated based on the initial condition. And the same way, if you substitute in the form of a formula or an expression that will account for, let's say, the current or the charge, it has to be a formula that already specifies the value of the K based on the given in the problem. So in this case, this should be your final answer, not this one, the one that has still the K, not this one wherein you're simply going to substitute the R, the L, and the V sub S here. It should be this form wherein the K is already known. And the only thing that is unknown, or the only variable present on the right side, is just the time. Now, in the second sample problem, you're given an RL circuit having an EMF this time, which is not constant. So it's an AC circuit. Resistance is given, inductance also, and this time an initial current value of 6 amperes. The first example has 0 for the initial current. You are still to determine the current in this scenario at any particular time. So it's noted again here that your voltage is a sinusoidal AC voltage source. So 3 sine 2t. Again, the ever fundamental equation of KVL. So the voltage drop across your inductor and your resistor should be the voltage across your circuit. And that is your 3 sine 2t. Now, the voltage drop in the inductor is expressed here in terms of the inductance and the derivative of the current with respect to time, and that of the resistor is IR, and this one being a constant is copied. If we want to express the circuit with the derivative in linear form, then we need to divide this dE by L. So if we divide by L, this would be your circuit, your linear first order differential equation. Now, if you will substitute the values for the R and the L, the V sub S and the L, this would be your circuit equation in terms of the current. This is your integrating factor. And if we will have it processed now, again, we have here the integral having the exponential function and the sign. So a while ago, I've shared to you a general formula for the cosine and an exponential function. This time, I'm sharing to you a formula in terms of the sine and the exponential function. So you process this one based on the formula here, knowing the constants that appears in the arguments of the exponential function and the sine function. So if you will substitute this formula on the right side of our differential equation, the integral that is, this will be your answer. But this is not yet your answer because you still have the K. You need to find what is this K. And we call this one, this equation, as the complete response of the RL circuit, just like I've shown to you the complete response of the RC circuit in the first file a while ago. Again, you could see that you have two terms here. One is exponential and the other set is trigonometric in form. So the first one is the natural transient or source-free response again, and the second one is the force or steady state response. So you have the exponential function appearing in the transient response, and you have the trigonometric function appearing in the steady state response. It was stated in the problem that at time equal to 0, the current is 6 amperes. So you have to place here 6 and you have to place here 0. 0 here, 0 here. That would allow you to determine the K. So your K is 6.0297. Then you go back to the original equation that you have set up and substitute the appropriate K values. So K value rather, because you only have one. So you place it in here, and this is already an equation that will let you solve for the current at any particular time for your RL circuit. Okay, this is for the RL circuit. So you see this at time greater than 0. Another method, just like the one that I have shown to you in RC circuit, is the equation that is already ready-made, doesn't have any DE that is appearing on it. Still the same, you have the I sub n and the I sub f here, and the determination of the values, the constant that are given in the problem. So you have the V sub m, you have the radian frequency. The radian frequency, by the way, is the constant that appears in the argument of your sine angle. I missed that one. This one, that's the omega. Okay, the constant that appears on the argument of your sine or your cosine angle. Your V sub m is the voltage that appears in your, where's the given problem? In here. The constant that appears before the sine or the cosine function in your AC voltage. That's your V sub m. Okay, I mentioning that a while ago. So you have 3, you have 2, you have 10, and these two are given in the, this one is given, so you just substitute it with this one. Again, you have the formula for the impedance and the power factor angle. You have to take note plus that the impedance and the power factor angle formulas for the RL and the RC circuits are not the same. Okay, they're not the same. So these are the formulas for the two. Then you just substitute the theta and the z in the formula that you have here. You have the z here and you have the theta here. So that's it. You have already placed it in here, but again, we need to change the k. So same as what we did a while ago. Substitute so that you'll find the k. So you have now your I equation similar to the first one. So method 2 does not use any DE, method 1 does. I'm sure this one came also from a DE or a simplified form of the DE, this one coming from the formula. Okay, so that's for the RL series circuit. So the first one is RC series circuit. I will make the most of the time, so I still have one here, 2 more files. So for the capacitor class, I've shared this to you already, the different formulas. For a source-free RC circuit, I've given you a sample problem on this also in the first file that I'm the one who gave you. Now, the total current in the total current leaving the top node must be 0. So we write that IC plus IR, this is the node that is referring to, is equal to 0. I'm sure you have, I'm not so sure if this was discussed in the physics of the CHE because their physics is only 1. Whereas the ECEs have 2 physics in their new curriculum. So if you have 2 physics, this particular nodal analysis in circuits is discussed in physics 2. I'm not sure about the CHE. So this one class is something that you need to know. Okay, when you do nodal analysis, the sum of the currents entering a node or leaving a node is always equal to 0. Always set to 0. Okay, and the current that is passing to the capacitor is subscript C, passing to the resistor is subscript R. We add the 2, and then whatever are these current expressions as discussed, the current in the capacitor is C dV dt, whereas in the resistor, it's V over R. So you have a differential equation now that is in terms of the voltage. So unlike the other differential equations, which is in the form of the current or the Q, this one is in terms of the voltage. So if we will process this, this is a separable differential equation. You have V equal to K E raised to negative T over RC, which is the natural transient or source-free response of an RC circuit. And it is analogous to that of the RL circuit. Amo ning iya sang RL, amo ning iya sang RC. As mentioned a while ago, in the first file I've shown to you, in the RC circuits, it's always the voltage that is being determine the voltage drop across your capacitor. In the case of the RL circuit, it is the current that passes through your inductor that is being required, and this is the one. So they inform they're more or less the same, only that in here you have the RC in the denominator, but this one is R over L. Now, if you substitute the initial condition that at time equal to 0, there's no voltage in the capacitor yet, or meaning your capacitor is initially charged, then you can have V sub O is equal to K E raised to 0. This one is 0, so anything divided, 0 divided by anything is 0. We copy the K, and this V is changed to V sub O, meaning that's at time 0. So for your capacitor, your K, this K now will be changed to V sub O. So this is now V equal to V sub O. Again, copy the exponential function. And if it's graph, that is your V against time. So at time equal to 0, your V is V sub O. And you see an exponential decay. You see an exponential decay in the value of your voltage across your capacitor. Okay, now if we will continue with the Q being equal to CV, let me just plug my laptop class. Okay, it's already low in battery. So if we have already here the equation for Q being equal to ZV, and the V is this, we just substitute, and this is your formula for the Q at time greater than 0 for our RC circuit. The C and V sub O product is merged into one representation, which is Q sub O, because this is your capacitance multiplied to the initial voltage, which is your Q sub O, taken from here, this one, and this. So we just specify the initial values for the voltage and the charge with subscript 0. So actually it came from this one. So this is now the charge in your capacitor at t greater than 0. The current through the capacitor is given by this formula. And by the way, this one is shared to you at the beginning part of this file. All the formulas that you have here. Okay? These are the set of formulas. So you can refer back to those formulas or write it down in your notes. That way you won't forget it later when you get the quiz or when you get the exam, because you're done with the quizzes already. Excuse me. So you have IC as this, the current in your capacitor. You have the derivative of the V. So the V that we have here, this V is differentiated with respect to time. So this is the derivative already. And your IC in your capacitor, or the current in your capacitor at any particular time, is given by this formula. The current equation can also be determined in terms of the Q. So you have the current here determined in terms of the Q. This one, the current determined in terms of the voltage. You have the voltage, this one in terms of the Q. And you can refer to this as the graph of the change in your V sub O over R. So as time proceeds, there's the value of which is asymptotic to this is time initial and this is after time t. Okay, so this graph was you just imagine, class, that you will turn this graph counterclockwise, and you will have this on top, and this is the initial time. So again, there's an exponential decay in the value of the V sub O over R in this case, because as t proceeds, or as time proceeds to t, you have the value here. Okay, you have the value reaching this particular line. It's asymptotic to this particular line. Whereas if it's approaching the initial value, the value is V sub O over R. I'm referring to the current. So this particular part of the, shall I say, the axis is the I, and this is your T sub O, and this is your T. After some time, your I will be approaching this value here. In here, it's negative V sub O over R for the I. Okay, then I think I will have to leave to you the rest. So I have one file here that needs to be discussed. So you just read it through. Everything is already in your canvas, and please read this as well. Just in case, I think you fully know that when we prepare for the exam, your teachers contribute problems. So it's not just being made by one teachers or by one teacher. So we share problems with one another. So for you to be best prepared, whether it's a circuit problem, whether it's a mixing problem, a decay problem, and what else? Newton's law of cooling problem, whoever gives the particular problem, in terms of fundamental principle, you are lacking none. You know the fundamentals, but I'm sharing this with you just in case it will be a little bit above the fundamental that you'll be required to answer later on in the exam. So your exam schedule is actually posted already. And if you have any question, if you have any clarification as to what you have read here and studied, you can always message me here in Canvas or in my messenger. Okay, class? So I'll hear from all of you. I'll see you when I see you. I'll, I'll see you virtually probably during the exam or before the exam. So again, everybody gets the exam, but the grades will be put on hold for those who are not able to settle their due for the month of October. Okay? Bye, class.
Thank you,
Thank you and
Miss.
goodbye, Miss.
Bye.
Bye, Miss. Thank you.
Okay, bye.